All right. Hi, everyone. Thanks for coming. For the sake of the camera, this is San Francisco MySQL meetup group. Tonight we have Andrew. He's going to talk to us about Sphinx. I'm not going to butcher his last name like I butchered some names the last couple of months. Our sponsors tonight, O'Reilly, they provide books. IGN, they provide my time in the facilities. Continuant and Percona are also sponsors. Aaron, do we have any other sponsors right now? No? All right. Don't forget, next month we have Hadoop. That's going to be a really interesting talk. I know it looks filled up, but we're going to increase the numbers a little bit to get some more people in. So join the waiting list if you haven't already. As always, we give the opportunity for people to announce other community events, or if they're looking to be hired, to hire someone, that sort of thing. Anybody have any additional announcements? Cool. Anyone else? All right. Well, with that, I'm going to go ahead and turn it over to Andrew. It's now 7 o'clock.
When you officially turn off the lights in San Francisco by 7 o'clock, right? Or is that just me and October and the rain? So thanks everyone for coming despite the rain. I was told that's a great showstopper for everyone living in San Francisco. So the talk is about herding Sphinxes. That is apparently a catchy name, right? So this is the actual plan that we're going to cover today. But then again, depending on you guys, we might just as well skip some of the bullets on the agenda and slice and dice and rehash the talk in any way needed. What is it? Louder? Louder? How's this? I might also try turning on my Russian accent. If that's any better with you guys. Oh. 1, 2, 3, 4. Okay. I'm hoping this is better then. So, well, this is the plan. Basically, from the very beginning to a few of the more in-depth things as to how the engine works internally. What do you do in this case? What do you do in that case? So I guess before we begin, I should ask you guys for a little show of hands. Who knows what Sphinx actually is and who actually tried it in production? Okay, that's a little less. So I suppose we should not skip the getting started in 3 clicks and core concepts and so on and so forth. Anyone? Anyone thinks that we should skip? Let me put it this way. Does anyone think that we should skip the basic stuff, the very basic stuff? Okay, a few people do. Most of you don't. Well, let's get started. So, what is Sphinx? Well, apparently, besides being a giant statue somewhere in Egypt, it's also a bunch of things. It's actually a documentation system for Python, and I think there is a speech recognition project called Sphinx just as well, but the one we are going to talk about tonight is the open source source server, aka a program that you, well, use to do full text searches. What is supposed to be different about Sphinx? And to give you a quick overview too, well, we suppose it's fast. We claim it's fast enough, scalable, relevant. It's written in C++, just like MySQL is geo-licensed and can be and is distributed under GPL version 2 or under the commercial model. And the biggest instance of Sphinx that we know of, because with open source software, you never actually know who's running you and for what exactly. Anyway, the biggest known instance that we know of runs 300 million queries a day, and that's actually Craigslist.org. And the biggest known one in terms of document volume handles several tens of billions of documents, like 20 billion or 30 billion. It's never possible to squeeze the exact number out of those guys because they keep adding servers and documents and whatnot. And it's actually pretty easy to use because, well, the 2 basic commands that you really need to use Sphinx are as follows. You configure most of the stuff via the means of the configuration file, sphinx.conf, and for querying and actually even monitoring it to some extent, you can simply use the MySQL command line utility, because Sphinx actually talks MySQL wire protocol. So getting up and running in 3 clicks is just like this. You grab the distribution, and I only used the RPM sample for the sake of being a sample, because we actually package it for all the reasonable platforms. I mean, we have Red Hat RPM packages, DEB packages, Windows binaries, Mac OS binaries, and so on and so forth. Anyway, you get it, you install the binary package, start up the service. It comes with a few of the prepackaged sample indexes, sample full text indexes. You're more or less set. But apparently, simply getting it up and running is never enough. You actually got to use it. And this is probably the most simple way to actually use it. If you pay attention to the server version field, and which I highlighted for you, it says 202 something. So this is actually MySQL client talking to a Sphinx server. In fact, when I took this fabulous true color screenshot, there was no MySQL server even installed on that box. So this fabulous and amazing screenshot comes from a MySQL client talking to a Sphinx server. No MySQL server involved in that equation. It isn't even running. It does not need to be installed, and it's useful to have it installed, of course, because you would still want to use MySQL to store your data, grab it from MySQL, push it into Sphinx for the full text version. But in theory, you could, store your data in plain old text files, push them off to ship them off to Sphinx, and that would be it. So now for something useful, you probably want to run some queries against Sphinx just as well, and this is how you do that. You run something like very resembling a standard SQL statement, except, of course, it does come with a few extensions of our own. Namely, in this example, the wait function is an extension. This is something we use to return the relevance value as computed by Sphinx within the result set. And the match operator is our very own extension too. Because in standard SQL, I don't think there is even a statement for the full text matching. In MySQL, the proper syntax would be something like match against. In Oracle, as far as I remember, it's contains. So bottom line, there is no standard SQL, and we wanted to save a token first and to differentiate our queries against MySQL queries a bit second. So bottom line, this is how you do querying with Sphinx. Pretty easy, I think. And just one more bit about the queries and the stuff within the quotes, within the apostrophes, the pipe signs, that's actually an operator, a full text operator, namely OR, and of course there are a bunch more operators than just OR. We do, of course, support all the usual suspects, the Boolean AND, the Boolean OR, the brackets, and a bunch more operators. Now, another perhaps even more interesting mode of use would be not simply querying Sphinx indexes, but inserting to those indexes, but also writing data to those indexes on the fly. And we actually have two backends, so-called disk backend and real-time backend. I'll go into details a little bit further in the talk, but with real-time indexes, you can do something like that. You just insert the data into those indexes, and replace and update and delete are also supported, except update is a little bit limited, but anyway. And from there, you could do the selects instantly. So kind of a drop-in replacement for MySQL, kind of, because actually it's only going to replace the full text functionality bit, and at the same time, it's going to be somewhat faster than MySQL's built-in full-text storage, be it MyISOM or InnoDB full-text search engines. So, well, a quick recap. So what just happened? We used the vanilla MySQL client. It talked to search the server using the wire protocol reimplementation, and you can have the MySQL server running, but you don't need it, and Sphinx package does not depend on it, and you do not need any of MySQL stuff to build it. That's a common misconception. That's why I'm stretching this so much. And we ran a few queries using an SQL-ish syntax, but beware that we do ship with a bunch of extensions of our very own, and this is really SphinxQL, not standard SQL 92, because that would be a royal pain in the fingers to implement, way too much typing, all those statements and clauses and stuff. And of course, being a full text search engine, we definitely need to add a bunch of extensions which would let you control different aspects of full text queries as opposed to SQL queries. And there is a lot more to it. There is a lot more stuff that you can tweak and tune via the configuration file, the languages, character sets, data sources. All in all, we have like 170-something directives, and we keep adding those. And they are becoming more and more involved configuration directives. And on the querying side, SphinxQL is complete. Basically, everything that Sphinx can do, be it just querying or real-time changes to the index or generating snippets or doing facets, doing geodistant searches, all that fuzz is supported, and everything that Sphinx can do is exposed via SphinxQL interface. I think that at this point it's even more comprehensive than the historic Sphinx API interface. We do also as a side note, this is not on the slides, I think, we do also have a historic API, some kind of a custom API that we implemented for Sphinx a while ago. But, well, come to think of it, that was a mistake of the youth. If I could come up with the idea to implement the SQL interface in the first place, I guess the API would never have been born. But, well, the idea to implement SphinxQL came like 7 or 8 years later than that. And, well, we began with the API. We have to support it. For now, it's going to stick around for a while more. But, well, APIs and QALs and data sources and indexes, that's probably our very own Sphinx talk. So we really got to define a few of the terms in the book, if you will. And they are not many, really. So there are only a few core concepts that I wanted to talk about. One of the concepts is the data source. This is the definition of the, if you will, the location of the data that Sphinx indexer program is going to pull. And it can be either SQL or XML. In other words, Sphinx indexer can pull the data out of an SQL database. Well, most frequently MySQL, really, but in fact, any other database could work. We have installations running with Postgres, Oracle, I think even something more crazy like Firebird or DB2, but I'm not really sure about those two. Anyway, most of the instances are of course running MySQL, everyone is. Or the data source can be in the XML format. You define, in that case, you would define a path to a script which emits the data in a predefined but simple enough XML format, and Sphinx indexer can read that data from a script and can index that. We also have I'll show you guys the examples shortly. It probably will start making somewhat more sense. We also have a notion of full text index, and there is a big differentiator within the index. Within it, we do have a concept of fields which get indexed, full text indexed, and become searchable for keywords, but that data is not stored in the index itself. So if you have a field like a content field like Mary had a little lamp, once you index it, it will become searchable, and you will be able to match the document very quickly on any of the keywords in that field, Mary or lamp or whatever, but the initial string itself, the Mary had a little lamp quote, that will not be stored in the index. As as another side note, if anyone here cares about PCI compliance or something like that, any security issues, it's theoretically possible to reconstruct. In some cases, it's theoretically possible to reconstruct the original text from the full text index. In other cases, that's probably not even possible. I mean, we don't store the original text, we store the full text index, and depending on what settings you use, reconstructing the original text is going to be either pretty hard or even impossible at all. Well, just sidetracking, sorry. And another concept that we have is attributes. So as opposed to fields which get indexed, full text indexed, but not stored, attributes, on the other hand, get stored, and they actually live in memory. They get cached in memory, but they are not indexed in any way. They are used as an auxiliary, helper data, which lets you filter or sort or group your search results once you're done with the initial full text search. Basically, search for all the iPods. Now I need them sorted by the price. When you're searching for the iPod, say Nano, this is where the full text index kicks in. But when you need to have those rows you just matched sorted by the price, this is where you need the attributes. And finally, another thing about the full text indexes is that we have two backends here, actually. One of the backends is the so-called disk backend. It's semi-updatable. I used to call it non-updatable, but that's probably creating confusion again. It's semi-updatable in that you can update the attributes on the fly, but you can't really update the fields on the fly. So if document text changes, you cannot do anything about it with using a single disk index, but you can update the prices and the authors and any other metadata stored in the attributes on the fly. Or we have the real-time backend, which kind of fixes all that. Apparently, that comes with a price at a cost of a bunch of overheads. But, well, the real-time ones acts in a real-time way. I mean, the updates get executed in a few milliseconds. Another two things that you should be aware of are the concepts of, well, result set aggregation and rotation. This is mostly useful for the disk backend, and really dates back to not having a real-time backend, which is fully dynamic. They work as follows. In Sphinx, you are not limited to searching through a single index. You can actually search through many different indexes at the same time, and Sphinx is going to search all of those indexes, perhaps in parallel too, depending on how you configure it. And it's going to grab the results out of all those indexes that you mentioned in your query, one way or another. And it's going to aggregate those results and return you a combined result set. Meaning that even though disk index, a huge disk index, is monolithic and sort of cannot be updated, this is, in most cases, this is not even a limitation. Because you could shard your data and put most of it into the big archive index, which doesn't change much, and put the rest of it, the just updated recent part, into a tiny delta slice and re-index that slice from scratch, that tiny delta index from scratch, well, every single minute, or every 5 minutes, or every hour, depending on how frequently do you need the full text index updates. From there, you would simply issue a query which searches through two indexes at the same time. So instead of, in this example on the screen, instead of selecting everything from test 1, which from a single index, you could write something like select star blah 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 from test main, comma test delta. In that case, that would search for through two indexes, combine the results, and return the combined result set. So that's almost it. The final thing, the final term on the sheet is the rotation. Apparently, you don't want to take the search down while the index gets updated, right? So rotation is simply this. If the storage daemon is already running and the index files are locked, and you're rebuilding one of the disk indexes from scratch, and this still makes sense, actually. Even with the advent of the real-time indexes, it still might make perfect sense to use the disk-based indexes. They're simply quicker to reindex, and in some cases, you don't really need, real timeness, as in 1 millisecond latencies. So the rotation is simply the notion of creating a shadow copy of the index with all the new data in it, and then sending the storage daemon a SIG-hop signal which commands it to pick up the new data. That's it. So to reiterate, once again, data sources, aka we define where do we get our data from, full text indexes, which is our main data structure. This is our core. This is something we've worked with all the time. And within the full text indexes, we have fields which get indexed. You can search for keywords in them, but do not get stored. And we have the attributes, which are completely the other way around. They do get stored, but they do not get indexed. You can pick between the two backends, the faster and perhaps more optimized disk-based one, in which you cannot really update the text data dynamically, except you can work that around by querying multiple indexes and setting up a main plus delta scheme. Or if you want to spare yourself from all that hassle, you can use the real-time backend. And there is one more thing I'm actually missing. It's probably a good mental model to think of this stuff as a kind of an SQL database because, well, data source, basically this defines the snapshot source. Data source is something that defines a snapshot of your current primary database. Full text index is roughly equivalent to an SQL table. It sort of works, like an SQL table. Ditto for fields and attributes, except there are two different kinds of... they both map to columns in the SQL table, but they behave differently. And backend, well, in MySQL book, that would map to the storage engine. Yeah, that's probably way too much, buzzwords without any code. So this is the time. This is the right time to show you guys some, well, not really code, but configuration from the sphinx.conf file. So this is the simplest source, and this is really just the access configuration, so nothing big about it. The more interesting part of the source, and this really is a working source, so just 3 lines besides the access data. This is it. This is the complete definition. So we defined where shall we fetch the data from, which host, which user to use, and so on. This is the query that we use to generate our snapshot. And within that query, we need to be, because we differentiate between the fields which get indexed but do not get stored, and the attributes which do get stored but do not get indexed, we need to differentiate that. And also, on Sphinx side, we need to know what type of a column do we need to use on Sphinx side again. Because, well, theoretically, and even practically, we could infer it from the MySQL column types, except that would create a plethora of problems with all the other databases, and the inferer making subtle mistakes all the time, and so on and so forth. It's much easier if you guys simply specify what columns are actually attributes, and the rest of it, of all the columns, they get indexed as fields. So in this example, title and abstract, they are not listed as the attributes. They are not declared using the SQL ATTR directives, so they simply get indexed as the full text fields. And they become searchable. The simplest index definition is even simpler than that. You define a data source, which you pull the data from. Side note, you can define as many of those as you like to. So theoretically, scratch that. Practically, you could fetch some data from your MySQL database, some of it from the PostgreSQL database, some of it from the Oracle database, some of it from the text files, and combine all that stuff into a single index. And the index would be located at a path specified by, surprisingly, the path directive. It would create a bunch of files, like 7 or 8 files, using this as a base name and appending .sp something extensions to the name. And I also explicitly defined the character set type to be UTF-8, so kind of signal that I'm expecting the data to be in the UTF-8 encoding. That's it, done. the simplest source, aka a snapshot of the database, as the specific snapshot of the database, we will be taking and indexing the simplest index definition. That's it. And this is actually going to work. I mean, with 100-something directives, apparently there is much more stuff here that you can use, but the simplest ones are simple. Oh, and one more example for the real-time indexes. Actually, only a few lines change again. We have to declare a type, and by default, we use the disk backend. So you have to explicitly specify that you want to use the real-time backend. You still need to specify the path and the character set type and other text processing settings and whatnot. But in addition to, we don't have the notion of source here anymore, right? Because the we have that for the disk indexes, in which we grab a snapshot of the data from the database, index it, and make it searchable. With the real-time indexes, it's the other way around. We define it initially in the configuration file, and the first time that the source daemon is run, it notices this new real-time index definition, and it sort of creates the table. So the real-time index definition in the configuration file, think of it as of a create table statement, which will be used for the initial creation of the real-time index. Side note, corollary, if you change this definition after the index is created and populated with data, nothing is actually going to happen, because this is just the initial create table statement, the equivalent of the initial create table statement. Oh, and of course, you have to specify what fields and what attributes to use in the real-time one. So there, that was the kickoff. That's how you get started with Sphinx in 3 minutes. Grab the package, install it, use the MySQL client to play around with it, and define your very own indexes like this. Define your very own database you want indexed. Define your very own snapshot query, or define your very own real-time index with your very own set of fields and attributes and whatnot. And that's it. You're all set. But, of course, there is now much more to this than just setting up sources and indexes and living happily ever after. And the next chapter is speaking in tongues, aka all the text processing tools that you might need. Because, well, the first question you're probably going to ask yourself once you have set up your initial index, indexed your tiny database of like 10 million rows, and concluded that the searches are quick enough. Well, I probably need to tweak and tune this to my very own requirements. And the requirement number one is typically, dude, I don't speak your tongue. I need to, my database is in German or in Finnish. I need to add support for that language. Or you're indexing numbers in your default configuration. You're considering them legal characters. I don't want that. But on the other hand, I do want to declare the dash sign as a valid character. And much more. Well, the text processing tools. Everything text processing related begins with the character set table directive. This is the core of our tokenization, basically. The core of how are we going to break down the text into the actual tokens, keywords that we will be storing in the index. And this all started like 10 years ago, right? And even back then, there was a bunch of different languages and a bunch of different requirements, and implementing predefined presets for all the languages on the planet seemed a little hard. So instead of that, I went ahead and implemented the table directive, which lets you specify what characters exactly do you want to index, do you want to consider legal in word characters, and how exactly do you want them folded. So in this example, I'm mapping all the uppercase English letters to all the lowercase English letters. And I'm also mapping the Unicode code point number 1 to 3, and I have totally no idea what character is that, to the Unicode code point 4, 5, 6. And this example comes with a catch already. I do map the uppercase English letters to the lowercase ones, but I'm never declaring that the lowercase ones are valid and should be considered legal characters. So this particular definition, if copied verbatim to the configuration file, is going to index all the capitalized words, but it's not going to index all the mixed case words or all the lowercase words. To do that, we would also need to declare a range of A to Z lowercase in the char set table too. This might seem kind of hard, and it probably is, but at the same time, it's pretty flexible, because this way you could you have, well, character level granularity. For any given target language, you could create your very own character set table. If you want to fold the accented letters like A with all the crazy signs that they put on top of that A with the acute sign, the circumflex, whatnot, if you want those accents removed, and I personally do, you can do that via the character set table. You just declare all the mappings, and that's it. They all get folded to the A. If, on the other hand, you want to make your sources case insensitive, you can do that just as well. You do not fold them. You do not use the ASCII arrow, and you simply declare those letters as valid, but you never fold them. And lo and behold, your sources are now case sensitive. And so on and so forth. So basically, char set table is a huge transformation table. Everything that is mentioned in the table is considered a legal character, and it might be mapped to any other character. That's it. And everything which is not in the table is basically considered a white space. So this gives us a very flexible tokenizer that you can twist and tune to, well, any sort of the requirements you might have on hand, except that breaking the text into words is, well, just the tip of the iceberg, or maybe half of the iceberg, but there is a bit more to it. After we have broken down our text to the tokens, to the keywords, we typically want to do more about that. And these are the directives. There are actually a few more directives related to text processing, but these are the ones you would want to use most. So a quick run through all of the guys. Morphology. What is that supposed to mean? There are a bunch of stammer unit support, and we're actually working on a few more morphology modules for Sphinx, which basically normalize the word. So even in the English language, a single root form of the verb, for instance, run, could generate a bunch of different forms of that very same verb. Run, runs, ran, running, so on and so forth. If you do not want to differentiate between any of those forms, you want them normalized. That's exactly what the morphology processing does. That's exactly what the stemmers do, and a bunch of different stemmers are integrated into Sphinx. And this is also what the lemmatizers do. There is a subtle but important distinction between the two. I'll guess if anyone is interested in that, what are stemmers exactly and what are lemmatizers exactly, and how do they differentiate? I think that would be a good question for the Q&A session. But once you have applied the morphology processing and normalized like running to the a word form running to the original form run, all of a sudden you have now lost the original form running, and there is no way of telling that running was even ever in that document. For all the index keyers, it's run. It has no way of telling that the original form in that document was running, that it was not runs, that it was not ran, that it was running. To fix that, we have an index in the exact words flag, which is going to inflate the index size by approximately 2x, in fact, like 1.8x or 9x, but also the original forms of the word before the morphology processing, along with the normalized forms. So that's it. That's about it. That's like 99% of all the morphology processing that the average Joe, myself included, would want to do. Next stop, stop words. This is easy, really. There are a bunch of words that you want to ignore for the sake of the full text version, like a and the and I and you and whatnot. And not would probably also be in that list. What would probably not be in that list? This is getting complicated. Anyway, in stop words, you specify you can specify a list of the words that need to be ignored. Well, in fact, you specify a path to a file which contains the list of the words which needs to be ignored completely altogether when both indexing the text and searching for and querying the resulting index, searching for something, but that's it. Another file is the word forms file. And this is something yet different. This basically lets you define synonyms in your input data. So if, for the sake of the example, you want to map, if I'm running out of good examples here, say, if for some reason you want to map Obama to president in your index and lose the differentiation between the two, well, I guess no one would want to do that forever, at the very least, but occasionally that might be a good synonym to have. Anyway, if you want to map two synonyms into a single token, the word forms file is exactly what you use. This is basically a huge map, a huge token map, which gets applied both at indexing and querying time. Just like with morphology stuff, after you have applied the synonyms, there is no way of telling what was the original form. And unlike morphology, we don't yet have an option to include the original form in the index. Well, come to think of it, that might be useful, but come to think of it again, that was never requested. Oh, and also word forms lets you map whole sentences of tokens. And those are tokens, aka keywords after the case folding, the punctuation removal, and the white space removal. You can map whole sequences of those into a single keyword. Example, you could map something like core to duo to a C to D. Or you could, in addition to that, you could map something like E6600 to C to D just as well, because as far as I remember, E6600 is still core to duo architecture. Despite the fact that the second mapping, E6600, would map a single keyword to a single keyword, and in the first case, core to duo would be a sequence of 3 different keywords, that would still work, and both sequences of tokens would get mapped to a single synonym. Pretty useful for the e-commerce sites. That way you could create rather involved synonym groups in your index. Yet another text processing tool in our little Swiss knife is the exceptions thing. Now, all of the things that I have just talked about, the morphology processing, the stop words, the word forms, that's all fun and games, but all that stuff happens, all those past processing tools get applied after the tokenization step, driven by the character set table. So imagine, for the sake of an example, that plus is not in your char set table. Because normally, plus is not a legal character in your particular application. But at the same time, you do want to index things like C++ or C#. So there are 2 special characters which do not need to get indexed normally. But in these 2 particular scenarios, they do need to get indexed. And this now is a frequent situation at job sites. Those guys don't really want to index all the pluses and hashes which might be occasionally used for fancy CV formatting that the candidates would occasionally do. But at the same time, they definitely want to be able to differentiate between C++ and C# and plain old C. That's essential for them. This is exactly where the exceptions come in handy, because the exceptions are also a token-to-token mapping, except that exceptions get applied before the tokenizing step. So they are, by definition, case sensitive. They do not rely on the character set table anymore. They can mention the characters which are outside of it, and that's it. So they are also one-to-one mapping, but basically, while word forms work, word forms, stop words, morphology, all that stuff works on the tokens, on the result of the application of char set table to the incoming text, and breaking down the incoming text into keywords. Exceptions are different. They work before that. They basically work before the character set table and before the tokenizer and before the tokenization step. So kind of useful for job sites at the very least. Yet another thing and yet another useful thing and for yet another vertical are the blended characters. We see those used at two different scenarios a lot. I would say things like documentation sources, code sources, where it's not exactly clear whether or not things like underscore should or should not be a separator, and social data mining. So platforms like Radiance 6 and Board Reader and so on and so forth, people who grab a vast amount of data from the forums, Twitter, Facebook, all the social media resources, and provide data analytics platform on top of the data. So they were kind of happy about the blend characters directive when it was initially introduced, because what blend characters lets you do is define a list of characters which are treated as both a separator and a non-separator. And in addition to that, the blend mode directive lets you fine-tune what kinds of the resulting token will or will not be indexed. So, for the sake of the example, assume that the ampersand sign and the @ sign, the commercial @ sign are configured as the blend characters. If they were not, then there would be no way of telling. There would be no way of searching for A, T, and T altogether, because the ampersand would be treated as a white space, and the only thing you would be able to do is search for AT space T as a phrase, and that's hell slow. And in addition to that, being hell slow, it does not even produce guaranteed results. If you were searching for AT and T as a phrase, in addition to having to scan, having to scan through the entire huge document list for @ and another one for T, there would be no way of telling whether that sequence of two tokens was generated by the AT and T in the original text or by something else, like a sentence ending with an @ and then a stray T in the text. Because the punctuation would be all removed, there would be no way of telling. So blend characters are really a savior in this case, because this way both AT token and T token are still indexed. And actually, that phrase operator that I just mentioned with two keywords, AT and T, would still match the document. But in addition to that, the original token, AT and T, is also indexed as a single token. And you can search for that. And this is really convenient for the data mining applications, mining for crazy brands like, well, AT&T and M&M's and whatnot, different abbreviations like USAF, and Twitter handles just as well. This way, same story. You would define, you would want to define the @ sign as the blended character, and by the way, you could even tweak it to differentiate between the Twitter style mention, where the blended magic character, which gets interpreted both as a white space and as not white space, and an email, in which it's not in the very beginning. Yeah, that's probably enough about the blended characters, and we should still leave some stones unturned for the Q&A sections. And another useful tool, a couple of tools really, when it comes to text processing, are the index SP, which stands for sentence and paragraph, and index zones directives. These are easy though, somewhat easier than some of the stuff just before that. So index SP identifies the sentence and paragraph boundaries in the incoming text using a bunch of empirical rules which still work pretty well. They do differentiate between Mr. Someone and the middle names and a few other cases and actual real sentence boundaries. Well, they should fail. They can fail from time to time, of course, but like in 99% of the cases, they just work. Paragraphs, same story. When you're searching through the HTML, when you're indexing HTML and index SP as enabled, the analyzer is going to look at the block level HTML tags and declare them the paragraph boundaries. From this, you have the advanced sentence and paragraph operators enabled, and you can use you can run queries like find me all the documents in which Alice and Bob are mentioned in the single sentence, or within the same paragraph, or with the help of the index zones thing within a single XML element. So index zones is about indexing the locations of opening and closing XML elements, or HTML elements really, and then being able to query for something within those zones. So I really should have put in an example, but oh, actually I can put in an example. Goes like this. So imagine for the sake of an example that the index that was a mistake. That the index zones stuff was configured like that. What this does is says to is telling to Sphinx indexer that all the tags, all the HTML elements that begin with an H, say H1, H2, and so on, should be indexed. Their locations should be tracked. Once you do that, you can use the syntax like zone H1, find me something, and that's going to find everything. All instances of all the keywords limited to a given HTML tag. So again, this is really not your everyday tool. Most of the people out there would probably never need this. But for different verticals, different things, one or more of all these different things could be really useful. So for instance, sentences, paragraphs, zones, these tools are really useful when it comes to searching through huge documents like legal documents or SEC filings or something like that. Well, basically books. Think of books. You definitely don't want to match a book on the grounds that something is mentioned on the page 1 and something else is mentioned on the page 300 something. You need more control than that. So when indexing large documents, huge documents, and when you need advanced querying, you really need these two. When indexing social data stuff, which with brand names, Twitter handles, stuff like that, you definitely want blank characters. If you're a job site which needs to differentiate between C++ and plain old C, but still ignore a plus, well, exceptions is your friend. Ditto for word forms and stop words, which are useful when you need to create an ontology of synonyms for your indexing/querying job, except for stop words are probably the one directive which is generally useful in all cases, because with stop words, if you list the top, the most frequent keywords in your stop words, if you ignore them, throw them out of the index, you save a lot on the index size. And at the same time, you save a lot on the query time, because the huge list for the does not need to be processed anymore. This might or might not be acceptable, though, because Google spoiled everyone, and Google works nicely on a query to be or not to be these days. I do remember the time when it used not to, actually, when it used to, I think it used to throw away everything in to be or not to be. It used to throw away everything but the not. And it used to query for that not at GNU's website. GNU is not Unix in the title, on the front page, on a highly respected website. Now, GNU.org or FSF.org, sorry, used to be the result #1 for to be or not to be, even on Google. Well, these days, unfortunately, Google had spoiled everybody, so stop words might be something that you can or cannot use. But it's a good tool for speeding up things and reducing the index size in case you still can't afford to throw away those noisy words. And these days, frankly speaking, I have no idea what exactly would Google pull up as the first result for it to be or not to be query. But, well, yeah, in the good old days, that was FSF. That was kind of cool. So, yeah, that's it. A tiny slide, a lot of talking though, a bunch of tools that you could use for different verticals. There is probably no way you would want to enable all of these in all of your projects at the same time. That would be way too complicated. And moreover, you would probably bump into some very subtle bugs in Sphinx. Because there is no way we could test all the combinations of all the directives. I mean, come on. It's like 7, 8, 9 directives. 2 different options for every single one of them. That's 1,000 something variants to test that. We don't even have that much manpower. But still, in for different tasks, in different verticals, this is very useful. And a couple of these, like character set table, morphology, stop words, are generally useful. You definitely want to use char set table to define the languages, basically the languages, more specifically the tokens that you need indexed in search. You frequently want to use morphology because it's the natural language you are indexing after all, and querying for. And you would still, despite the fact Google spoiled everyone, you would still frequently want to use stop words because that's an easy way to reduce the index size significantly and speed up queries mentioning stop words significantly by, of course, ignoring those altogether. Now for the next chapter on the list. It's going to be somewhat smaller, though. The distributed magic. Now, I'm kind of structuring this talk as a super quick, but at the same time, complete journey from the very beginning to the very end. So remember, our first step was let's grab a package, let's install it, let's do some very simple queries. Done. Let's do some magic. Let's configure a Sphinx in a way that we need to configure it. Let's configure fancy stuff about our language. Let's configure fancy stuff about our morphology, blending characters, because our vertical is social data mining. Done. Now, oh, wait, what? We've just passed the 100 million rows per single index mark, and the queries are getting slow. They're taking a few seconds. That's unacceptable. We want to speed that up. Let's go distributed. How do we do that? Well, you do that like that. You divide and conquer. Conquered and divided. Same story here. A bunch of different directives that you should be aware of. And you want to use in this case. So all the distribution, all the parallel work, this is highly parallel work. All the parallel work in Sphinx happens through the notion of a so-called distributed index, which basically is nothing more than a list of indexes. That's what it is, really, internally. It's even handled internally as a sophisticated way to declare a list of indexes. And those indexes can be local, aka reside on the formally, excuse me if I'm falling through to, well, way too formal definitions. That's a side effect from one of my previous lives. I mean, the university stuff. Anyway, this is just a list of indexes, and indexes can be either local, residing on the very same machine, or they can be remote, residing on a remote Sphinx node, on a remote search daemon node, running on a different server. But in both cases, whether you want the work parallelized within a single machine and utilize like 8 cores to search through like 8 different shards of an index, or if you've got yourselves for some weird reason 8 different one-core boxes, different physical boxes, and you want to parallelize the work over those boxes, distributed index is your friend in both cases, except that you use 2 different directives to define those guys. Local is apparently used to define a local index, which is a part of the current distributed index. Agent, same story. You use agent to define a part which is remote, resides on a different box, and you specify, and this is probably the second time I should make amendments to the slides on the fly and punch in an actual example. But you punch in something like agent equals host 123 colon port ID and then the index name. That's it. As simple as that. Okay, give me a second. Oops. Or not. Seems kind of locked or something. All right, I probably better not touch it. Someone up there is giving me that signal. Oh, and there is the agent black hole, which is not really useful for any real work, but very useful for load testing and bug fixing. Yeah, bug fixing is sometimes a complicated story. It does nothing, really. On the master side, it just says this. Forward any request which flies into the current index, forward it to that agent, and dismiss that agent completely. When searching for local indexes, well, of course, unless the query crashes, the master master process, which queries all the local indexes and all the remote nodes, is going to wait for all the results to come back and aggregate them. This is not the case with the black hole directive. It's one-off. I shoot the request, the master node shoots off the request and forgets about it completely. So this is useful for load testing, for testing the rolling changes. You set them up on one nodes, on just one node in the cluster. You set up the black hole node on one of the nodes, and reload the indexes quickly. And by the way, if you send the sig hop signal, the distributed index definitions are going to be simply refreshed. It isn't needed. It's not required to stop and restart and start the server again. So yeah, kind of useful for the crazy situations. Another thing which actually comes into play when working with distributed indexes is the plain old SQL query directive, because you want to put the different shards of the data on different boxes or different shards of the index. And SQL query is how you do that. Basically, you just put different limits on your primary key on different machines. On machine number 1, you would want to index rows 1 to a million, for instance. On the machine number 2, rows 1,000,001 to 2,000,000 inclusive. You do that via the SQL query. You're all set. Another important directive is dist threads, and this is how it works. Normally, this is the default historical behavior, and probably the wise thing to do anyway, is to use a single core to search through all the local indexes defined in the distributed index. So, to reiterate, even if you have like 24 indexes defined in your distributed index and a 32-core server, it will still utilize just one core to search through all those local shards sequentially. Well, that's the safe thing for the server to do. We can't assume that we can't actually assume that your server has got more than one core. But at the same time, this is not really the best thing for you to do, and you should hint the server and let the server know just how many threads can it use to parallelize the work. And this threads is exactly that directive. You use it to specify how many threads, how many parallel threads can the server use to process a sharded index. That's it. Another two options, two pretty important options, I would say, related to the distributed clusters are the timeouts, the connect timeout and the query timeout. So when you declare something using the agent directive in Sphinx, it reaches out to the remote node and it waits for a little bit of time. It does create a separate thread to do that, but it still waits for a few milliseconds, a few hundred milliseconds actually, until the connection succeeds. And from there, it waits more until it gets the results back, which can be a very bad thing. If one of the boxes just went down and your timeouts are set way too high. So for the sake of an example, what if the connection timeout is set to something insane like 30 seconds and one of the nodes goes down? All of a sudden, all of the queries from the entire cluster begin responding in 30 seconds plus. This is, well, not the best way to configure your cluster. And what you want to do is remember about this thing and set the connect timeout and the query timeout to a reasonable, small enough value. And frankly speaking, perhaps the default, the demo values in our sample configuration file are even way too big. As far as I remember, they are at something like 1 second for the connection timeout and 3 seconds for the query timeout, which seemed all right like 7 years ago. But these days, I would suggest to punch in something between 150 and 300 milliseconds for the connection timeout. And the query timeout, that's a wholly different story. This really depends on the speed of your particular queries, on your particular cluster, and those can be very different. Some people run, 2-word queries against a tiny collection. Some people run queries which mention like 5,000 something keywords and complain that their server is running out of memory. Well, yeah, one more seemingly unrelated thing, this second one. The first one was SQL query. It really is related to the distributed stuff because you use it to set up the different shards of the data. And the query log format SphinxQL is useful in the distributed case for an interesting reason. Our default log format is human readable, as in clear, short, and concise. It's basically timestamp, the number of matches, a few facts about the query, but not the complete query description and the query text. Kind of like the Apache log, only even shorter and even more readable than that. Well, it's nice to read through, but it's really not nice when it comes to debugging. And SphinxQL format is a totally different beast. It still begins with a comment with the timestamp and the number of matches and all the useful stuff. From there, it formats the entire query as a valid SphinxQL statement. And after that, it includes a bunch of additional debug information like the I/O time, the CPU time, the timings for the individual remote agents in that distributed index, and that's why it's important for a distributed case. If one of your indexes, if one of your agents is too slow, query log format equals SphinxQL plus, well, the actual query log is your friend. In addition to that, we have yet another addition to the slides is due. I sense that. Sorry, guys, I was preparing this for the last 2 nights, every single night. Another thing that you want to use is the show status operator in SphinxQL, which shows you a bunch of different counters and includes the timings and the error ratios and everything you want to know about the remote agents. But basically, that's it, and this is kind of nice. So you can actually set up a distributed cluster using only a few lines again. If you want to split your work over several different cores within a single machine, all you need to do is shard your data, create 4 different index definitions, and index definitions are like, what, 3 lines each? You will also have to create 4 different source definitions, which are also like 3 lines each. And you would have to use different ID ranges in all of these guys. From there, you would have to define something like that. 5 lines too, actually, except that those would be for 5 different lines. They would go like type equals distributed, local equals shard 1, local equals shard 2, 3, and 4, and that's it. From there, you would search that index with dist threads 4. Lo and behold, you're using 4 cores in parallel. Or you could ship away the shard number 2 to a different machine, and instead of going local equals shard 1, local equals shard 2, define something type equals distributed, local equals shard 1, agent equals the other box, shard 2. That's it. You're utilizing 2 machines. So kind of simple. And there are really a few tuning knobs that you definitely want to use when building up a cluster. These threads to control the number of threads which are going to use, which you allow the server to use within a single query to search for all the local indexes, and the timeouts for the agents. And you probably want to enable the more detailed log format to investigate the problems in case they pop, but that's it. Okay, so the question was, what do we do on the Amazon when the network is held slow typically, but fast on occasion, and maybe the connection timeout is going to be 60 seconds? Well, two things, two different comments here. First is a personal preference. You don't really want to run a highly loaded cluster on Amazon. You probably still want to run it on bare bones, not on the cloud provider, because in my experience, the differences in performance are huge. You see like 10x difference in between the Amazon slice and the equivalent and the seemingly equivalent VM you run on your local machine. Even if you limit it to 2 gigahertz, a few gigs of memory, and blah, 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 still the differences in latencies are crazy, even within a single machine. This is not even accounting for all those network issues on Amazon that you just mentioned. And second, with connection timeouts in seconds and minutes, well, the queries become non-real time anyway. So you need to do something different about this anyway. And this is a tough problem to attack right now. We're working on a few things. I'll mention that in the end of the talk. You could do something about it with by mirroring the agents and specifying different timeouts. So if one of the agents fails, if Amazon is being slow, or there is a network congestion in your data center, the master node could switch to a different index. This is not in the trunk yet. Oh wait, this is not in a 2.0 release series yet, because there were no new features since for a few months now. But this should be in the trunk, actually. And a complete change of subject. Scans, as in full scans in Sphinx and math. And that's like this, brute force. They are brute force. Well, full scans are brute force. If you're not using enough, well, just use more cores, throw more machines, except that when doing full scans, you probably want to be wise about it and sometimes avoid the full scans. But there are situations, actually, in which you cannot simply avoid a few scans. Like one does not simply avoid a full scan at all times. There are situations in which my favorite model example here would probably be eBay. Well, not eBay per se, but eBay-like websites, auctions, say price aggregators, all the websites on which the typical query, which happens like 90% of the time, maybe even 99% of the time, is a query which uses a bunch of constraints on a bunch of columns, and every single constraint is not selective. Think Craigslist, for example. This probably is a good one too. Find me all the cars in San Francisco. Find me all the apartments in San Francisco which have 2 bedrooms and a price within that range. If you put the data into the actual database and search for and put a constraint on column number 1, okay, equals San Francisco. Column number 2, okay, this is the price range. This should be in this given range. Okay, column number 3, number of bedrooms. This should equal 2, except, oh, it can also equal 3. On every single column, the condition is going to be highly non-selective. Well, not really highly, but moderately non-selective. And unless you have a really good covering index, and for this vertical, frequently you cannot. Unless you have a really good covering index for that particular query, your queries in MySQL or any other relational database are going to slow down to a crawl, because every single condition would only be referencing way too much rows. And unless the database can go really fancy about it and intersect the indexes and pull up the rows you really need really quickly, the queries are going to be terminally slow. Basically, well, in some cases, it's probably better to use the full scan. And, well, despite that Sphinx is a full-text storage system, we actually have full scans. I resisted a lot. I mean, this was definitely not a design decision from day one. Everything began with the full-text core, but eventually users actually started doing this fancy trick. They started injecting all their rows, all the rows they were indexing with a magic keyword, like all the rows. And from there, they were searching for all the rows, and then adding the additional filters on top, like where price is in that range, and I don't know, the bedroom count is in that range, and the landlord is not a dig flag is true, and all those highly non-selective conditions, stacking. In addition to that, the users kept bugging me about, well, having to add that all the rows magic keyword, because that's not, well, that was easy to work around, right? The concat, you simply add a concat when indexing your data, and you search for that all the rows keyword, but A, that's kind of messy in the configuration file. It's not really the right thing to do. And B, it definitely does add additional overheads. And I resisted for a while, I think a few months, maybe even a year, but eventually I converted and saw the light and realized that A, if the query actually runs 10x faster, well, maybe not 10x faster, maybe just 2 or 3x faster than the equivalent MySQL query, and B, if after that change you do not have to maintain 2 different code paths anymore, one code path which hits Sphinx when the user punches in a full text search, and the other code path which hits MySQL in the unlikely event the search does not have any keywords in it, well, that's a good thing to have. So eventually I implemented the full scans on Sphinx too, and they are pretty fast because, well, remember the part in which I bragged about Sphinx index being a kind of a snapshot of a database? The attributes are essentially an in-memory snapshot of the database and a slice of the database. You pick up some attributes, the only ones that you need to additionally filter or group or order your search results by. Anyway, frequently you only pick a fraction of the attributes from the database. And essentially you create a snapshot when creating the full text index, and you have that snapshot anyway. And if it's useful for an additional query type, not just the full text query type, why not use it? And this is exactly how we use it. How we use those attributes. When you do a select where, order by, group by type of a query without the match condition, without the operator which actually does the full text search, this is exactly what we do. We go into that huge in-memory blob sorted by the ID. We scan all the rows in that blob, applying all the conditions that you just added in the where clause, order by clause, and so on and so forth. And depending on the type of the query you run, this can be like from 100x, maybe 10,000x slower than MySQL, because apparently you definitely don't want to do this for the query which goes like select star from my index where ID equals this. Well, doing a full scan to retrieve a single row by what is supposed to be a primary key is not the wise thing to do. And with Sphinx, the query Sphinx, select star from something where ID equals something is basically still a full scan, basically, because, well, in that particular case we could indeed optimize that query, but basically that would be a full scan. But at the same time, if the query is right, if you are replacing a query which is only able to utilize a not really selective index in MySQL, or even worse, if that's kind of a report, some kind of a report that you're moving from MySQL to Sphinx, and if the data is there anyway, I mean in Sphinx, in the Sphinx index, and if that report can be moved occasionally, you could see a nice speed up on your queries. And full scan on our end could be up to a few times faster than the equivalent scan in MySQL. I guess everyone skimmed through the benchmark results here on the slide right now. So that was just some kind of a task table with some kind of an index associated with it. Not really much attributes. I think that was something like the Wikipedia index, really, with the page IDs and the page lengths and something else like page titles and the last modification date, something like that. And an imaginary query, which an imaginary full scan query on MySQL side executed for a couple seconds, on Sphinx side for less than 1 second, with a total of 2x boost. This is a highly synthetic example, because in all reality, for this particular query, you would have just created a covering index on ID and touched, or actually touched an ID in MySQL, and you would be done with it. The query on MySQL side would be instant. But, and there is not really too much space on the slide, but if that query went like select all from all my auction items where condition number 1 equals this and condition number 2 equals that and condition number 3 is in that range, that's a totally different story. And we used to see a lot of that stuff. Well, not really a lot, but we used to see a bunch of users and clients moving that type of queries from MySQL to Sphinx. The data is there anyway. We are essentially scanning it in MySQL anyway. There is nothing we can do about it anyway, because there are like 100 columns in our MySQL database, and the users are typically adding conditions on 2 or 3 out of those columns, and there is no way we could create pair-wise covering indexes for all of the combinations of the 2 columns out of 100. You would bump into the 1000 index limit in MySQL, and then again the insertions would be crawling on MySQL end. So in that case, Sphinx is, well, not really the savior, but could be used to alleviate that crap a lot. Oh, and there is another thing, in a complete change of subject again. Our bottom line, our expression engine is somewhat faster than that of MySQL for some reason. And of course, for the ultimate performance, you would want to use if your expressions are super complicated, you would want to use a UDF, both with MySQL and Sphinx, and you can actually do that. And actually, our UDF interface is almost like the MySQL one. So it takes you maybe half an hour to hack in a UDF, which to hack in an example, to hack in a new UDF using our example. Anyway, back to the expressions. So the dynamic expressions, the ones you put in the select list, something like select are A multiplied by B plus C and so on and so forth, these are somewhat faster. And this is the synthetic, wrong, and not really good benchmark that I used, which still gives you an idea of what kind of a speed up you could expect sometimes from Sphinx. So I ran a couple of queries, like the minimum value of an attribute on both Sphinx and MySQL, and these are our baseline. This is something that I subtract from all the other times to isolate the expression time alone. And these are all the different expressions that I tried. And this is my favorite synthetic example. Apparently, MySQL doesn't optimize, or at the very least, the version that I used back then when doing that benchmark did not optimize the divide by 1, divide by 2, divide by 3 expression at all. And apparently, it was doing the honest division by constant every time for every single row it was evaluating, resulting in a huge slowdown. And Sphinx does that. Sphinx does a bunch of simpler expression optimizations like constant folding and a few more. But anyway, depending on how complicated your expression is, you can expect a speed up of a few times in the expression calculation alone, and then some on top of it, if your query was that bad query, that scan type, or that super slow index read in MySQL, which converted to a reasonably fast scan in Sphinx. And once again, this is not a silver bullet. Not all of the queries could be converted this way, but sometimes in some verticals, like the auction sites, like at the auction sites that I mentioned, this would be your #1 query, the query which is really responsible for like 90% of the load on the entire website. And I peddle in the auction sites here for a reason too. The model example is basically the Turkish eBay. Those guys were actually one of the major major influencers, if you will. The model example which finally convinced me to implement the full scan support in Sphinx side. After a few chats with their developers, I got convinced. They really were running a billion page view website. And that was a few years ago too. So they're probably bigger by now. Not sure if still using Sphinx though, but I'm hoping they are. And apparently it works for them, given that I'm not hearing from them. Anyway. To put aside the mumbling, back to the expressions and scans, take out number one. If your query is doing a lot of scans or a too slow index rate, pulling too much rows on a condition, you might consider Sphinx scans. Might be worth it. Might be not, because if you're doing something like select star from Sphinx index where ID equals this is going to be hugely faster in MySQL. We are not a database quite. Not yet. We won't do the primary key. We won't do a seemingly easy query like a primary key lookup very well. At the same time, we would do a scan pretty well because we don't have all the overheads associated with your typical transactional engine. At the same time, we would cope with the complicated math expressions pretty well compared to MySQL. So they are generally faster, as evidenced by the simpler formulas like a plus b multiplied by c, and they are optimized better, as evidenced by these two latest examples. So give it a shot, might be worth it. And there was something else that I wanted to add. Yeah, of course, why wouldn't it? You can definitely run a scan on a distributed index. It works just in the same way. It would what distributed index actually is just a list of indexes, right? Both local and remote. And what the master node, which carries the distributed index definition, actually does is simply it forwards all the queries to the nodes, to all the local indexes and to all the remote nodes mentioned in the distributed index specification. It lets them do all the work, divide and conquer, and then it grabs all the results back, aggregates them all together, does a quick sorting pass on top of that, and that's it, and passes back the final result set back to the application. Corollary, it doesn't really matter what kind of a query you are running. As long as all the nodes in the cluster are able to work on that query, they can even be different versions of Sphinx running on top of different versions of indexes, and actually even having different schemas in that index, because those schemas would be minimized and only the intersection of the columns would be returned in this case. But anyway, I would say it's resilient, if you will. That's actually a side note I should have put in the distributed section, but one of the design decisions behind the distributed indexes was to be resilient as possible. If I can give you some result set, perhaps a partial one because half of the nodes in the cluster do not respond, I give you that. Except that it comes with a warning that, well, half of the nodes in the cluster did not respond. And the result might not be complete, it might not be, perhaps it's not really what you are looking for, but in any case, if Sphinx was able to get some result, some response back from the nodes, it will give you that. Oh, and back to the expressions, I just recalled what I wanted to one final thing that I wanted to mention about scans and expressions. So scans, typically slower, really, but occasionally up to like 3x faster when it comes to scans. Expressions up to, well, 40x on the synthetical examples, faster on a synthetical example, but at the same time like 6x faster on a reasonably simple formula like a plus b multiplied by c. So if you're doing a lot of complex math on MySQL side, it might be worth it too. But all that magic happened on a single core. All these benchmarks were carried out on a single core. And with Sphinx essentially taking snapshots of MySQL database or a part thereof, it's going to be somewhat easier to parallelize that work and improve your latency even more than that. I mean, with MySQL, you are to emulate something like this with MySQL, you would have to create a federated table. I mean, what would we assume, for the sake of an example, that for some reason we cannot build a covering index on this stuff? Perhaps on the grounds that we are sourcing the result set not just by touch, but by a couple of columns. And that couple of columns is different because our analytics want to run like a gazillion different reports. Assume, for the sake of an example, that we still have a 2 mil row table. What are we going to do in MySQL? How can we speed that up in MySQL? There is, well, no good way to do that. With many combinations of column pairs, the covered index path is a no-go anymore. We have to revert to full scans. And full scans are comparatively slow. And we kind of can parallelize that in MySQL, but for that we have to create a federated table. And I'm here, and as far as I know, the federated plugin, the federated engine, is still as flaky as it used to be in 2004. So, well, yeah, I mean, I'm not following. So yeah, so perhaps it's not supported anymore. In Sphinx event, well, the data lags, of course, because it's essentially snapshots. But it's easier for you to generate shards of those snapshots. And on every single part, the scan is going to be somewhat faster. And in the end of the day, for some very specific query kinds, you might be squeezing out as much as a 10x, 20x speed up out of sharded Sphinx index compared to a single core MySQL table. It's like magic, but then again, this is a very special case. If any single MySQL query would speed up 10x, I would probably be calling it something different and not talking about a full text search engine anymore, but working on a full-blown database solution. And so that's it. Scans, faster; expressions, faster; sharding, easier; total potential speed up, anywhere from 2x to 10x. Your mileage may vary. And yet another chapter and a complete, or, well, not really complete. Let's peek under the hoods. How exactly does the engine work? What's on the inside? What keeps all that stuff running? Well, this is what. So there are going to be a couple tiny slides here just as well. First, the engine insights. How does all that magic happen? The basic data structure is really very simple. It's called the inverted files, and it's basically 3-tier, if you will, or 2-tier. Everything begins with a huge sorted dictionary. We store all the keywords that you index in a big, bad sorted dictionary. And every entry in that dictionary is the keyword itself plus basically a pointer to the list of all the documents, all the rows associated with that keyword. That's it. And in addition to that, because it doesn't end with the Boolean operators like and or, we also have to keep the keyword positions within the documents. We need that for two things. First, for matching, because if you are searching for a phrase, it's not enough to know that that both keywords are in the document. We also need to know their relative positions, and for that we need the positions. And in addition to that, we need the positions for ranking, because all the advanced ranking formulas are going to be based on the positions. That's it. That's actually the structure used for all the searching. It's as simple as that. So in theory, it's nothing more than a huge dictionary plus either a tiny list in case there is just one document in it, or a huge list in case the keyword in question is something like a or the or at. But it's a dictionary, and there is a document list attached to every keyword in that dictionary, and there is a position list attached to every keyword in that dictionary just as well. And we use the document lists to do the Boolean matching. We use the posting lists, aka hit lists, to do the phrase, proximity, sentence, paragraph, and all the other location-based operators. Keyword location, I mean, not the user location. And that's it. Oh, and on top of that, kind of auxiliary to the inverted file structure, there is a big bad attribute blob. And it really is a blob. We grab all the data from MySQL and we stuff it in a simple linear order. This is our ID, column number 1, 2, and 3, and 4, fixed size rows. We sort it by ID, we keep it in memory. We need that for, we can't really afford any other structure there too, because we need the lookups by the ID to be instant. So as quick as possible. And they are as quick as possible, because actually the internally, it's not even a binary search. It's faster than that. Anyway, the underlying data structure is very simple. Dictionary, lists of files and lists of rows and positions within the rows. And the reason behind keeping those separated, the document lists and the position lists, is that if the query can be satisfied without even looking at the positions, we don't touch that list at all. So if you're running a Boolean query which only needs to know whether Alice and Bob were both mentioned in the document, we don't even touch the position lists and save you a bunch of, a bunch of IOs. If you're, however, looking for a phrase, Alice and Bob, we have to read in more data and look up those positions. So the 30,000 feet overview on the indexing is as follows, as displayed on the slide just as well. It all begins with the source text. On top of that, we apply a few filters to that source text. There is an HTML, a built-in HTML stripping thing, which stripping/parsing thing, actually, because it's the very same piece of the code, which is responsible for eliminating the HTML or XML markup and identifying the tags which need to be indexed as paragraphs or as zones in the documents. In addition to that, we now let you in the current rank to define a regexp which will be run before any of the indexing operations on the source text, and of course the same regexp will be run on the application side just as well. So basically this is just syntax sugar, right? In theory, you could pre-process the data before feeding the data to indexer, and you could just as well pre-process the query before feeding it to the search daemon. But having that stuff handled by the engine is just so much more convenient. So there is a filter on top of the source text. Then there is this convoluted tokenizer I spent so much talking about, driven by the character set table and then modified by the morphology unit, and then modified by the stop words, by the word forms, by the exceptions, by the blended characters, by the ignore characters, by the n-gram characters for the CGK processing, and by all the magic that I forgot because I can't be bothered to remember all the 200 configuration directives. It breaks down the source text, the filtered source text, into the keywords. Those keywords go into the dictionary. Remember the data structure. Everything begins with a huge sorted dictionary. That's where the keywords get shipped. So the dictionary keeps track of, basically keeps track of all the keywords, assigns them the temporary numbers that we are using internally while indexing. From there, we simply do a two-pass sort because, once we break down the text into keywords, the data we have on hand is basically a huge, an insanely huge number of tiny rows, which go like document ID, word ID, keyword position. And that data is naturally clustered by the document ID, right? Because the data flies in document by document. And the word ID is basically random because it's a different word every time. And the keyword position is a scanned-in. And the inverted file, well, in order to be searchable quickly, we need a sorted dictionary, and we need a sorted document list and a position list. So we take the data, internal data. This is not real SQL rows. This is the mental model, if you will. This is our internal representation. During the indexing, we convert the document to this temporary representation of document ID plus word ID plus every keyword occurrence within a document. Sorry, we convert that to a tuple of document ID and keyword position. It comes it comes naturally sorted in this particular order, except that we need that data sorted in different order. So we do an old boring two-pass merge sort described by Knuth like 50 years ago. And we resort the data by the keyword first, and then by the document ID. And voila, we have the the inverted index. This is how the indexing works. There is nothing, conceptually, there is nothing more to it. Of course, the devil's in the details, and there is a bunch of different details. The tokenizer is insanely complicated. It's probably the most complicated part of the indexing pipeline. And there are a few complications around the attributes too, because we have to fetch them from the database. We have to bind to the documents. We have to create that blob. And there are a few more and more complications, but conceptually, this is how it works. It all begins with the text, some filtering at the top. We break it down to the keywords. We sort everything by the keyword. We sort within the keyword. We sort everything by the document ID, compress it using a special codec, compression, decompression unit, store that to disk. Oh, and yeah, this would probably be a good time to mention that Sphinx is completely standalone, and our indexes are plain old files residing on the disk. So the index is just that, a blob of, it's nothing complicated. It's not like a few pages in the IBData1 file, plus a bunch of metadata in the MyISM table, in the system MySQL database, which is hell to migrate. And hell to shrink in case you forgot to add in a DB file per table initially when you were configuring the server. It's much simpler than that. It's just a bunch of plain old files, and you can move them around freely around the boxes and probably even across architectures. So not really a complete change of subject, but singing to the same tune, searching. How searching works, well, same story here. All begins with a query parser, which is not a big deal unless you stuff, unless you pass it a huge query which goes out of stack. So the most complicated queries that we have seen in the wild were like 5,000 to 10,000 keywords. They were data mining type of queries with a lot of different clauses and conditions, and those queries ended up simply running out of thread stack space, because the default thread stack on Linux was, I think, 64 kilobytes at that particular server, and that was not enough to simply go and iterate over that tree, not to mention to evaluate it. So yeah, we ended up implementing the thread stack directive, one of the 200. It all begins with a query parser, creates an evaluation tree in which the nodes are basically the keywords, and the leaf nodes are the keywords, and the intermediate nodes are all the kinds of the operators on top of that node. But mind you, the full text operators, and or, and phrase, and sentence, that kind of thing. Not the filtering, grouping, not the where, group by, and order by clauses. That happens later. So the evaluation tree is basically doing the Boolean matching on top of the keywords. And it's lazy, like everything else in Sphinx. We try to do the least possible amount of work that we have to do to evaluate the query. So if the query doesn't need to touch the positions, it will try very hard not to do that. So the evaluation tree is responsible for doing the Boolean matching for all the ands and ors and phrases. On top of that, we apply, once we did the Boolean match, or a full scan, by the way, we apply the filters, the where clause on top of those results. And after that, because the filtering phase might have just thrown out 99% of the data, we don't want to do anything more complicated before the filtering. And we do ranking of the results based on the keyword positions within the document, and perhaps based on some complex math, depending on how complicated your ranking function is. We do that after the filtering. And once we did that, once we have everything computed for a match, we do the sorting and grouping of the results, aka order by and group by on top of the result set. Oh, and of course, all the expressions, all those select expressions that I mentioned a little bit before, they are lazy too, meaning that if the expression is not used in the filter, it's going to be, or in the order by phase, or in the group by phase, it's not going to be computed until the very final stage of the calculations. This is exactly why I needed to add the sum and average operators when benchmarking the expressions. Otherwise, Sphinx would just not have done anything. It would have postponed the calculations, and it would have only carried out those expression calculations for a tiny subset of the rows actually returned to the application. So, yep, the engine insights. Everything begins with a dictionary, a huge document list, an even huger, if that's even a word, position list, and on top of that, a blob of attributes, which we use to look up the scalar attributes used for where and where by, group by. That's the data structure. Indexing, source, tokenize, sort. Indexing is probably the simplest thing in all this magic. And searching, everything begins with the evaluation tree and so on and so forth. So a little bit more about the query insights. The most important thing to understand here is that there are different costs associated with the match processing at different query stages. There are Boolean candidates, aka I just grabbed a huge compressed document list for, I don't know, John, and another one for Doe, and I need to intersect that list. That's in the core of the full text matching, this operation. The list intersection when we're talking about the AND operator, or the list, the merger, acquisition. Well, yeah, first the acquisition, then the merger. Yeah, right. First we acquire the list for John, and then we merge the list for John and the list for Doe. And that's actually a quick operation to do, too. I mean, a Boolean query which honestly scans through two big enough lists, like a few 100,000 document lists, when working on a query like the I on a 1 million post collection. That query actually completes in like 80 to 100 milliseconds. And in that time frame, it's able to decompress the both document lists and honestly intersect them, and even scored the result in 500,000 matches. So it's kind of quick. Once we have done that, the Boolean candidates are not yet matches because there are associated filters on top of them. So for every candidate which passed the Boolean condition, which matched the full text query, we have to take its ID, go to the attribute blob, look it up, check the filtering condition, and perhaps throw it away at this phase. And the lookup is, well, it's pretty quick, but it's still limited. We can only, even though it's faster than a binary search, it's actually a hash combined with a binary search, and it's very quick. It's still capped at a few million lookups per second. I never benchmarked the exact number, so I would theorize anywhere between 5 and 15 million lookups per second. So when doing the filtering, the engine will have to do all those lookups for every given candidate row and do the filter check and perhaps throw it away out of the result set. Corollary, if you have a very selective filter, like assume for the sake of an example that you're indexing say 10 million different blog posts from different authors, from different bloggers, but every single blogger is not that prolific. The typical blog, he might have, on average, say he would have like 10 or 100 blog entries, or maybe a few thousand. But anyway, the condition on the restriction on the author ID would be very selective. So because of that, you would want to put the blogger ID into the full text index. Index that as a virtual keyword and actually index that and use that as a speed up. Because the other way around, you would need to scan the entire collection, but not really full scan, but search, index search through the entire collection, and then do the filtering on top of that. But if you put a keyword with if you put a magic keyword with the author ID into the index, you don't need to do that anymore. The filtering sort of implicitly happens at the earliest stage possible when intersecting the document list, and that's a great speed up. Guilty as charged. I have that benchmark data, and the changes, the differences in query speed are really huge, like 20x, and that's the difference between 10 milliseconds and 200 milliseconds. I just forgot to put them into this presentation. Ditto for ranking and ordering and grouping, but I was stressing filtering so much because there is little you can do about ranking and ordering and grouping. As long as the matches you have all match the full text condition, as long as they all match the where clause, there is little you can do about it. Well, these are the matches. This is our result set. We need to process it. We need to order it. We need to group it. There still are a few tweaks about that too, but there is little you can do to optimize them that much, which is not the case with filtering. So basically, if you have a highly selective condition and you kind of want that indexed, it might be prudent to put a magic keyword into the index and use that so that the rejection, the filtering, happens at the earliest and the most efficient stage possible. The Boolean matching phase in which the document lists get very quickly intersected. Oh, and there is a bare bones optimizer in it too, which is able to recognize a few things. Apparently if you if you specify a few keywords in the query, it makes sense to reorder them internally and evaluate them in different order. It does that. And if you pass a bunch of queries in a batch, and those queries are only different in their grouping or ordering clauses, in their group by or order by clauses, it makes sense to only run the full text query once and simply submit the results to the different sorting objects, sorting queues. And the optimizer is able to do that, and this is exactly how we do facets. And I think this was this is a limit with Solr in which you can't really, you start bumping into, you have to predefine. I didn't write that myself. That's a retail, so I might be lying a lot. But I heard that you have to predefine all the facets, and at some point you start running into limits. This is not the case in Sphinx, because you don't have to predefine anything. You don't have to predefine your facets, if you will. We don't even have a notion of facet. We have a notion of a query batch. And we look at that query batch as a whole, and we do any of the optimizations that we can do. If we can optimize, if we can identify, if we see that the entire full text query is a common part, and we can optimize it, and we can optimize that common part, we do that. We simply execute the full text query once and submit the results to a few different order by clauses, basically. And in fact, if you pass us a query batch, there is a different type of an optimization which is able to identify common parts within the query or within the batch of the queries and optimize that too. Temporarily cache the results for a subquery within the query and reuse those results. This, again, is probably not making sense for like 95% of all the users out there, myself included. We definitely don't want to use that for our very own website, but for social analytics types of queries, those killer guys which fire like 5,000 different keywords in all the different variations, this makes perfect sense. A specific query which we used for testing this was went like this: Barack Obama Alaska, and Barack Obama California, and Barack Obama Texas, and so on and so forth. It made perfect sense to execute the Barack Obama phrase part once and cache the intermediate results and reuse those results across the 50-something queries, because there are 50-something states in the United States, or so I was told. Okay, so speaking of explaining the tools to profile the queries, we don't yet have a good plan for a good explain, but I would say this is because our plan for a query is, well, static. Everything mostly depends on the queries, on the frequencies of the keywords, and you get those along with the results set. You fire a query, you run an additional show meta statement, and it gives you the frequencies of the keywords back. And this is basically the one biggest influencing factor in the query time. What were the frequencies of the keywords involved? This is what makes your query fast, or very slow. The frequencies of the keywords and the frequencies of, and the number of the matches. This is it. These are the two defining factors. We don't have we don't have many different execution strategies for every given query. We have all the kinds of fancy optimizations, that's true, but we don't really have many different plans for the query. They all begin with the very same tree, essentially. If you give us a bag of words, the only thing that we can do is keep scanning the document list for all those keywords and keep intersecting those lists and processing the matches as they come up. This is our only plan. So yes and no. No, we don't have a full-blown explain just yet. Yes, we are planning to add something which provides you with a little bit more insight than that. And to an extent, you can infer an execution plan based off the statistics of the keywords and the number of results. Question? Okay, so the question was, is there a way to control ranking? That's, well, this yes, and it's probably much more flexible than anything else you've seen before. We have the expressions, they're pretty quick. We expose all the internal factors, and there's like a dozen factors like TF, IDF, minimum IDF within a field, the first occurrence of the best span of keywords, and more weird stuff like that. We expose all those factors, we let you script the expression and build yourself your very own DIY ranking formula. And of course, it can also refer to the document attributes. But that's what the select expressions can do. The difference between that and the ranking formula is that the ranking formula has the access to the hardcore, low-level factors, which basically only exist for the duration of ranking a single match. That's the difference. That's well, it will probably take me too long to explain all the ins and outs of this subtle difference, but basically, yes, you can create yourself a very sophisticated ranking formula. Okay, there are just a few more things about the insights that I wanted to mention. Okay, that would probably be sufficient if I speak quickly enough. So, yes, there are two things to it. First, we have the so-called unigram characters. So in that tokenizer, the character set table I mentioned, you can specify a character class for Chinese, Japanese, Korean characters, and they will be detached, and every single character will be indexed as a single keyword. And from there, our default ranking formula pulls up the phrase matches higher. It ranks them higher than just the bag of word matches. So this is kind of good enough approximation for Chinese searching. And if that's not sufficient, I know that someone in China actually created a fork, integrated Sphinx with some kind of a segmenter for Chinese. Well, apparently that works even better for them. Unfortunately, I don't speak Chinese at all, so I'm in no position to, well, evaluate the both approaches. But basically, out of the box, you can specify a list of characters that you want indexed as unigrams, aka a single character should be detached as a single keyword at all times. And from there, you can rely on the ranking formula, which pulls up the phrase matches higher to pull up the more relevant results higher. And if that's not good enough, try that fork. Frankly speaking, I don't remember its name. Okay, so where the real-time index would be useful. This kind of resonates with a few lines on the RT insights that I had. So what is the real-time index actually? It's kind of useful to understand how it works internally. And internally, in fact, it's all based on the same old big monolithic batch disk index, which works, well, the disk index used to work by taking snapshots out of the database and very quickly re-indexing that data, creating an index structure on top of that. The real-time index works differently, but in the end of the day, it's based on the disk, the same old disk index too. It has a memory arena, so-called RAM chunk, in which all of the real-time magic happens, basically, without going too much details. And it's a fixed size arena, so you can figure like a 1 gig arena in which is used to store all the real-time index updates. But eventually, that arena overflows. If you, for instance, push like 3 gigs of data into that index, well, apparently at some point the 1 gig arena is going to overflow. What happens then is that the manager, the real-time index, is effectively a combination of disk chunks, a bunch of different disk chunks, plus a memory chunk, that arena that I just mentioned, plus a manager, a bunch of manager code on top of that, which automatically handles all of the hassles for you. It's going to flush that arena to disk and convert it to a disk chunk and sort of activate that chunk seamlessly, all seamlessly. And from there, it resets the arena and starts populating the in-memory arena again. So in a sense, this is kind of like creating a huge disk archive and tiny deltas manually with the disk-based indexes, except it takes manually out of it. Because these deltas would be sort of equivalent to automatically creating an arena-sized delta as you push the updates to the real-time index. And there is also the write-ahead log, which we call the bin log for both brevity and the desire to confuse everyone, for recovery. So every transaction that you push to Sphinx gets logged in the binary log first, and if the daemon crashes, it's going to replay the log and bring itself back to the well, non-crashed state. So it's sort of transactional too. Well, and that's it. That's probably not even the 30,000 feet overview, but still. When is this useful? I would say this is useful when you need the absolute, when you need the indexes to be absolutely dynamic. When for some reason you need the full text updates, the changes in the index text to be available in the search results in a few milliseconds, really. I don't think they do. As far as I remember, they use the disk-based indexes because that really is dynamic enough for them. Even with the huge batch, monolithic, blah, blah, blah disk indexes, first, you can still update the attributes on the fly, and you can very quickly flip the flags, change the prices, change the stock counts, and so on and so forth. Even with the disk-based ones, you can't change the text with those disk indexes, but you definitely can change the attributes. And B, if the delta is tiny enough, remember we can query as many indexes as you want to in one go, in one query. And if the part of the data which changes very dynamically is small enough and can be re-indexed quickly enough, you can get away with the disk indexes. And that's exactly what happens at Craigslist. They simply rebuild a delta every few minutes, and that's sufficient for their business requirements. The ads are dynamic enough, but they don't really have to be available in the search results in a few milliseconds after they were published. For that, for that kind of an indexing lag, for a few millisecond indexing lag, you need the real-time index. And by the way, it also might be, just might be, more convenient to program for, because it sort of eliminates all those hassles with deltas and keeping track of the data ranges which need to be put in both main and delta parts, and manually scheduling the cron jobs which would reindex the data, and so on and so forth. So reason number one, if you need the absolute minimal indexing lag. Reason number two, it might be more convenient to maintain, maintenance-wise. Let's see. Oh, that's actually almost it. So there are a plethora of different presentations as to how should you tune MySQL or PostgreSQL or Oracle or DB2 or whatever. Sphinx is unfortunately different. Well, there are still a lot of directives that you should tune depending on your requirements, but performance-wise, pretty much everything is going to work reasonably well out of the box if you get just the two directives right. And both most important directives are all about the memory limits, the memory arenas. First, with the disk indexes, there is the memory limit on the indexing arena that it is allowed to use, and for both for historical reasons and to protect those of us who are running on 32 meg VPS servers. Even these days, it defaults at 32 meg. So if you're indexing like a few megabytes of data, a few gigabytes or terabytes of data, you definitely want to raise the memory limit. This is the option. Well, the question is moot about the memory limit here. It might make sense to bump up the defaults in the configuration file. Then again, I do know for a fact that there still are instances running on a very tiny, on a very small VPS boxes. Ditto for the real-time indexes, except that the memory limit directive is different here. Absolutely same story, and this is actually also the indexing arena, and sorry, my dictionary seems to be getting swapped out at this hour of the night and the rain. So absolutely the same story here with the real-time indexes and that memory arena. If that index is expected to be small enough, you want to configure it low and keep the defaults low. If you expect to push a few gigs or terabytes into that arena, you also want to raise that limit. And it's important performance-wise, but not killer anymore. I mean, the indexing program, the indexer is definitely going to work, even with the tiny arena. It's just going to be slow. With the default 32 meg arena, it's going to be way too slow, even for indexing a few gigabytes. But if you bump it to something reasonable like 128 or 256 megs, it's going to become fast enough, and bumping it any further doesn't make much sense. Ditto for the memory limit in the real-time index, except in this case the situation is more severe. If you keep it at 8 megs and push like 8 gigs worth of data through that tiny 8 meg window, you end up with 1,000 of different disk-based chunks, and all of a sudden that manager that orchestrates all the RT work, all the real-time index work, now has to search through 1,000 different indexes for every given query. In the trunk, this is possible to fix. You would simply need to run the optimize statement on that index, but, well, it's better to get these two settings right first in the first go. Bottom line, the two directives that you definitely must tune for any given instance are the memory limits for indexing and for the real-time indexes. Then, depending on whether or not you are using the distributed index, whether or not and what your query profile is. The distributed setup, the agent connect, query timeout, and the retries settings might be of use. The defaults are probably not very reasonable these days anymore. And in certain query, for certain disks, depending on what kind of a disk subsystem you are running, it might make sense to tweak the read buffer and read unhinted I/O buffers, because they were basically tuned for a plain old platter disk, not an SSD, not a decent RAID. So if you're running off a decent enough RAID subsystem, it might make sense to reduce those buffers to the lowest possible level, like 32 or 64K, and keep all the I/O scheduling and all the caching to the operating system, because it's probably because the operating system would probably do a better job. Ditto for running on SSD. But if you're running on a plain old disk or software RAID, the default values are probably good enough for you. Bottom line, not very much tweaking advice when it comes to performance and config directives. That's before we don't have much to tweak there. That's because, well, the out-of-the-box performance is, well, reasonable and decent enough. And that's almost all, yeah. I just wanted to mention a few of the crazy things that we're currently working on. Some of them are in the current rank already, as opposed to 2.0 release. Some of them are being worked on and might or might not make it to in the next release. We have added the skip lists to our new index format, and they basically speed up the query evaluation a lot by a factor of 1.5 or even 1.7x on my tiny 1 million block past everyday testing collection, and even more, and much more than that on synthetic examples, in which one of the keywords is the, and the other keyword occurs like 2 times in the entire collection. With skip lists, we are basically able to skip the evaluation of the entire document list for the keyword, which was not the case before. We are working on high availability tools. The option to define the mirror agents for an option to define groups of mirror agents in the distributed cluster, and a few more options to tweak dynamic load balancing between those mirrors. It's probably going to give a lot of headache to us occasionally when some of the empirical magic about the balancing goes wrong and the cluster goes maxed out, but, well, we'll live and see. 2 more interesting, curious things that will be coming in the next months are the better morphology support, stemmers versus lemmatizers, aka morphology unit which makes occasional mistakes versus a slower morphology unit which makes much less of those mistakes. Another interesting forthcoming thing is support for JSON objects within the attributes. So kind of a free schema. You would right now our schema with the attributes and fields is essentially relational, and we are going to remove that restriction by adding the support for JSON object within a relational column. And there is some work on the relevance front. There is some work on the real-time index front. We're implementing double buffering so that the index, so that the flushes during the inserts, which have just overflown the memory arena, do not stall everything else for a few seconds. We've implemented the optimize operator, and as usual, we've done a lot more. So the complete changelog is probably going to be like 50 to 100 entries, and it doesn't make sense to recite it all. Recite the changelog aloud. But bottom line, we have done a bunch of cool stuff already. It's already in both 2.0 and in the trunk, and even more exciting fun stuff is coming. And that's actually it. This was supposed to be the time for the questions, actually.